about Chris that I really appreciate. One is that he was very welcoming to me when I first joined this community back in 97-ish when I was a grad student. I think we can all say the same, that he's been very welcoming to all of us. And the other thing I appreciate is how in many of his talks he's able to present an open problem that is very accessible sounding. And he's not embarrassed or ashamed to say the simplest possible thing he doesn't know how to do. And not everybody is willing to do that, but I always appreciated it. So thank you, Chris. So this talk is about minimally supported frequency wavelets, and the question is whether they're minimally supported in frequency. We'll see what that means in a second. So here is the outline. So a wavelet is a function such that dilates and translates form an orthonormal basis for L2, right? We'll be thinking in terms of the characterization via the Fourier transform, right? So this is the characterization that the modulus squared of the Fourier transform tiles by dilations, and it tiles by translations, and it has this additional TQ property that's a little bit odd. If this is the first time you've seen it, this probably seems a little like an odd condition. So let me draw a picture to kind of explain this. So I'm going to draw a picture of the modulus of C hat, and then I'm going to have on the negatives too. So what you can do is you can take pretty much any function you want in between 1/3 and 2/3, right? So this is f of c in between 1/3 and 2/3, and I'll pick some c naught here. Then if I am looking at, say, this first equation, then the sum of the squares has to be 1. So that tells me that, right, this squared plus this squared has to be 1. And if you look at it, right, that means it has to be something like this. Okay, so we have here, I've got a f of c naught. And that tells me f of 2 times this. This is just the square root of 1 minus f squared of c naught. That's what it has to be, because the sum of the squares has to be 1. Then we say, okay, now let's look at the translations, right? So this squared plus this squared also has to be 1. So it has to look something like this. So here, f of c naught minus 1, same thing. All right. And finally, I can come -4/3, -2/3. I can either say I have to satisfy the dilation condition, or I have to satisfy the translation condition. These turn out to be the same over here. And it just says that I have to have f of 2 c naught minus 2. This has to be back to f of c naught. Okay? So when I arrange my function values like this, you can see what it's saying is that the columns have to, the sum of the squares of the columns have to be 1, right? This squared plus, and this squared plus this squared has to be 1. And the sum of the squares of the rows have to be 1, right? That's what the two conditions are saying. And then TQ, right? This is saying that the columns have to be orthogonal as well, right? That's what TQ says, is that this times this bar plus this times this bar has to be 0. Right, so that's what TQ is saying, is that the columns of this matrix have to be orthogonal. Okay. Right, so that is how you can interpret the Fourier transform equations. So we're going to be interested in so-called minimal supported frequency wavelets, MSF wavelets. And those are particular wavelets where the modulus of the Fourier transform is just the indicator function on a set. Okay. That this seems to be the simplest possible case. We get the indicator function on a set. And then there's a theorem. Well, first a definition, right? We have a definition of a wavelet set is a set that tiles by translations and by dilations is a wavelet set. And the key fact is that these are the same thing. So C is an MSF wavelet if and only if the Fourier transform is supported on a wavelet set here. And if you want to think how we could construct one of those, right, I could have started with 1 here, right? And that would be 1 here. I would get 0, I would get 0, and I would get 1 here. Right, so this would tell me that negative 4/3, negative 2/3, union 1/3, 2/3 would be a wavelet set. And that would correspond in my picture over here to taking this diagonal as being 1s and the off diagonal setting those to equal 0. Right? That's what that would correspond to here. Alternatively, I could have made this 0, right? In which case these would both be 1 and this would be 0, and that would correspond to taking that diagonal. Okay, so whichever diagonal I take, I would get a wavelet set. Okay, there are plenty of other ways to do it, but this is kind of this is the one I want to be thinking about. Is like this. Okay, so I'm not 100% sure who came up with the terminology of MSF wavelets. I think it was probably Guido or Eugenio. I'm not sure. No. It was not. Okay, so I thought it was probably Guido. Oh, yeah. Okay. So this no, the measure is 1. Yeah, negative 4/3 to this is 2/3 and this is 1/3. It's a 4. It's a 4. It's a 4. Yeah, it's a 4. I had to think carefully because the thinking part of my brain turns off when the talking part of my brain is on. And so I was afraid I'd really messed this up. I had to think very carefully. Okay. Right. Right. So it was Guido Weiss. That's what I thought. That's who I associate the term with. He called MSF wavelets that because the support has the smallest possible Lebesgue measure, right? As Emily quite rightly noted, right, the measure of this cannot be less than 1, right? So they're minimal in the sense that they have the smallest possible Lebesgue measure for the support of any wavelet, right? You can, that's not hard to see. You could, I'm not gonna, yeah? Yes. Right. So right on, just on cue. Right. So I was at a conference at WashU, I believe, and I think it was part of the Frog group. But I know Guido wasn't part of that, but I think it was associated in some way. And I remember Dave asking this question. Yeah. Okay, I couldn't remember exactly where it was. Was it at DePaul? Okay. Right. So okay. Yeah. And so Dave asked, well, okay, wait a minute. Minimally supported to me means if you take something that's not a MSF wavelet, you can find a different wavelet that has smaller support, right? So in set inclusion, minimally supported in terms of set inclusion, which is a different thing. And I remember, if I remember correctly, Guido and Dave went back and forth for a bit before they finally understood one another. So I don't want to go over this too quickly because it's definitely a thing, right? That yes, but the question is, are they really minimally supported in the sense that if I take anything else that's not a wavelet that's not an MSF wavelet, can I find a different wavelet that has support strictly smaller? Right. This would be, to me, a more natural definition of minimally supported frequency. And if I said something is minimally supported in frequency, this class, that would be what I would have meant. Not to speak badly of Guido at all. I mean, okay. I shouldn't have said that probably, but that is probably what I would have meant. Okay. So the easiest way to prove that MSF wavelets are minimally supported would be to answer this following question positively, which Martin and I have taken to calling Larson's problem. I hope this is okay. All right. You just asked it. I mean, yeah. Well, yeah. If C is a wavelet, must the support of the Fourier transform contain a wavelet set? Right. So this is the question. So for example, for this one, right, it does. This wavelet does. But okay, is this in general true? And that was the question. So I'll just point out, right, that the characterization theorem says that the modulus squared tiles by translations and dilations. So we're asking, in particular, whether a non-negative function that tiles by translation and dilations, does its support contain a wavelet set? Right. This would be a strictly stronger question than, because we also have TQ that I'm never exactly quite sure how to incorporate TQ into these arguments. So this is a strictly stronger question. Okay. So there are several motivations beyond just nomenclature, right? Just that naming conventions. So there's my main motivation is that there's a lot of current interest in tiling via multiple actions. Primarily, people are interested in tilings via translations by multiple lattices, right? This is the thing that most people are interested in if they talk about tiling via multiple actions. So like the Steinhaus problem, so Han and Wang, this was whether there exist Gabor frames for every pair of lattices that with the correct volumes, right? That they showed that it does. The most recent issue is Kolonsakis-Grepstad showed that in fact you can get a bounded set which does this, and not just any set, but actually a bounded one that tiles by any two lattices with the correct volumes. So this is a pretty active area, and I see this as fitting in that framework. Just where I'm considering two different actions. I'm not considering translations along lattices. I'm considering translations with lattice, and then also dilations, right? So it's a similar type of thing. The other motivation was, I think Dave had a program of constructing wavelets, and Guido did too, well, not via operator theoretic interpolation, but trying to construct as many wavelets as possible using wavelet sets as a building block. And kind of, if you wanted to see how far that could go, one thing you might need to know is which wavelets, which their support in the Fourier domain could be written as the union of wavelet sets. If you're trying to build a wavelet via wavelet sets, you probably want to hope that the union of the wavelet sets equals the support of the Fourier transform. And finally, I've just been interested in wavelet sets my entire career. So this is something that's just inherently interesting to me. Any question about wavelet sets is always interesting. Martin and I have a paper that will finally appear this year, I think, where we characterize this in higher dimensions. Okay. So let's talk about some partial progress. This is from 2002. Joma and I showed that if you have a wavelet with small support in the sense that the translations only self-intersect at most once, the dilations only self-intersect at most once, then you can find a wavelet set contained in the support. And Martin and Joma showed that it's true if it's actually an MRA wavelet, then you can find a MRA wavelet set contained in the support. Okay. All right. So it's one where the dimension function of the associated wavelet is one. Yeah. So if you take the union of the negative dilates, that also tiles the line. Okay. So I'm going to talk a little bit more about the result that Joma and I had. So the way we proved it is we partitioned the support of the wavelet into these sets. So we partitioned it. We have a set that has nothing else, okay? And then we have these blocks here, okay? So, and the way to read this diagram is that anything on the same row is equivalent via translations, just like here. Anything on the same row is equivalent via translations. Anything on the same column is equivalent via dilations, and nothing else is. Right? There are no, I can't translate this and intersect this. That's just there are no other ways around it. So the key was to partition the support like this, and then once you do that, you can just take again the diagonal here, and that will be a wavelet set. Or you could take the anti-diagonals, I guess, right? Or you could mix and match, right? Whatever you want to do, right? So but as long as you take some sort of diagonal here, then that's going to be a wavelet set. Okay. So with no further ado, the theorem that Marchin and Joma and I proved is we ignored the TQ condition completely mostly because I don't really know how to incorporate it. And we said, if you have a non-negative function that tiles by translations and dilations, for example, the modulus of c hat squared, then its support contains a possibly non-measurable set that tiles by dilations and translations. So we haven't solved the problem because we don't know whether it's measurable, but you can definitely get at least a set that's non-measurable that tiles by translations and dilations. Well, when you see the construction, you will see that we definitely can't prove that it is measurable. I mean, yeah. Yeah. So, yeah. Yeah. So, right. So this is our main result. So what I wanted to do a little bit is talk a little bit about some of the ingredients in the argument. The main ingredient is doubly stochastic matrices and a generalization of Birkhoff's. I don't know how many people know Birkhoff's theorem for finite dimensional doubly stochastic matrices, but there's a generalization to infinite doubly stochastic matrices that we need. Yeah. So those are the main ingredients. Okay. So just as a reminder, a matrix is doubly stochastic if its rows add to 1 and its columns add to 1. So we're squarely in that category here. The rows and the columns add to 1. And then it's an old result that a matrix is doubly stochastic if and only if it is the convex combination of permutation matrices. Right? So permutation matrices are the natural doublet, are the basis for they're the extreme points of all, I put it that way, of doubly stochastic matrices, and you can get any one by just taking a convex combination. In particular, you can always find a positive diagonal, right? Because you take any one of the permutation matrices that are in the convex combination, that diagonal is positive, right? There's no limiting. It's just a finite convex combination, so it just works. Okay. It was an open problem for quite a few years, a long time ago, how to extend that to infinite matrices, and it was solved in the late 50s, and then by Kendall, and then Isbell in 1960. So they got the extreme points of the doubly stochastic matrices indexed by an infinite set, and then it's a little bit more work to say that actually then there's also a positive diagonal. It's maybe not as completely obvious that would happen if you in this infinite setting, but it is true, right? So there will be a positive diagonal. Yeah, that's what I mean for this. Yep. Okay. So I'm just going to give an overview of the argument, right? So we have a technical thing because all of our tiling conditions are almost everywhere, right? And so just believe me that you don't have to worry about that. We can find a set where it holds like pointwise and be done with it and not think about that again. So that's a technical step. And now we construct equivalence classes via dilations and translations. So we have 2 points are equivalent if they're related in this way. Okay. And now, for each equivalence class, right, we're going to build a doubly stochastic matrix. So what we're going to do is make sure that the modulus of c hat squared is doubly stochastic in such a way that each row consists of integer translates. Each column consists of dilations, right? And there are no other relations between point. The only time you get relations between integer translates is if they're on the same row. The only time you get relations between dilates is if they're on the same column, okay? We'll put aside exactly how you do that for a second, but that's what you do. And we want to ensure in the end that this Aij, right, that this matrix equals as a set this equivalence class. So everything in this equivalence class is contained in this matrix eventually, right? So this is kind of crucial. Okay, so once we have that, we apply Isbell's theorem to each matrix separately, and we get a diagonal for each matrix separately. We union all of those together, and that is our wavelet set. So getting back to the measurability question, right? So what we've done is we've split this set up into uncountably many equivalence classes and chosen a subset of each equivalence class, right? And that sounds like a recipe for possibly getting something non-measurable to me. Right? I mean, I definitely don't see how to prove. I mean, this proof, I am convinced this proof will not work to show it's measurable. Right? I'm completely convinced of that. Yeah. No. Okay. Yeah. So this is it. This is the overview. I have some slides here, kind of giving a picture of the how you build the matrix. I'm not sure how useful they'll be, but okay, we'll give it a try. So so I'm going to start with some. This should be C naught probably. We start with some C naught in the equivalence class here. Okay. You look at all of the C plus Ks, right? You add that to your row here, and you ensure, right, at this point, you take all the ones, and you're now ensured that the sum is 1, because you just take all the everything in the support, you just add it, okay? Once you have this, then you just build now you build up the dilations, right? You add these red ones, okay? And now the sums of these dilations has to be 1, because I've taken everything I could, right? You just take everything you can, and that's it. But now, maybe these I could translate them. So you have to do this iterative process, right? So now maybe there were 2 more that I could have gotten, and then maybe I'm done at this point. I mean, just for the sake of argument, say, okay, I have filled up the support. I mean, there's everything else is 0. I don't think that's actually possible, but okay. So I filled everything up, and we have a doubly stochastic matrix here. Right. So here we have a doubly stochastic matrix. And then I take my diagonal, which here I have colored. Oh, it's a complicated one. So this is a diagonal. Okay. And that's a diagonal in the matrix. Okay. And so you would take that. And in practice, right, this might be one block of your matrix, and you have other blocks, like what happened in the picture with from 2002. You could have like a block structure. And in fact, this isn't even how we do it at all. I don't know why, because this is how I think about it, and I think how I'd want you to think about it for now. But we have actually a different, a complicated looking formula that it takes me every time I look at it like half an hour to remember what it says, and I'm always convinced it's wrong. So I didn't think that was really the perfect venue for presenting this, but I think it's actually correct. But okay, the one that's getting published is the correct one. I think that was correct. This one probably not right. It's probably formally wrong what I've written here. Right? But this is the way to think about it. Okay, so that is it. So I have some open problems here. None quite as easy as easy sounding as some that Chris came up with. Yep. So yeah, so so just the measurable version of our results. So if you have a non-negative function that's measurable, it tiles by translations and dilations, must its support contain a measurable set that tiles by translations and dilations? I don't know, you know. And I'm sorry? F, because here F is playing the role of modulus of C hat squared. So you have any function that tiles by non-negative function, or you could take signed function. I mean, I also don't know the answer to that. So, but this is the most natural one. Take a non-negative function, tiles. Must its support contain a measurable set that tiles by translations and dilations? I don't know the answer if you add these conditions, right? That Joma and I used to prove for wavelets, right? Because we definitely used TQ. And that, like 100%, we used the TQ for our wavelet stuff. I don't know if you can add this extra condition, whether you can do it. The original problem that Larson proposed, so does the support of C hat contain a measurable wavelet set? That one's open. If you want to make it, if you want to handcuff yourself, you could say, well, let's not be satisfied with just containing a wavelet set. Maybe we should try to build one that contains a wavelet set whose associated dimension function is the same as the original wavelet, right? I mean, if you don't, these days, probably, I'm not going to take a poll. How many people know what dimension functions are? But back in the day, they were really popular. Yeah. So. And then, once you kind of have this notion that this question that, okay, set functions that tile by multiple actions, question, do they or do they not contain sets that tile by those same actions, right? You can imagine other questions that you could ask. I mean, I'm not going to ask them because I thought about them some, but I don't know enough to pose them as a question, but I mean, you can come up with lots of questions on your own related to different actions that not dilations and translations. Okay. All right. Well, that's it. Thanks for your attention.